A faint cosmic whisper, almost lost to time, held the power to shatter our understanding of the universe. These forgotten signals are ghostly echoes that have quietly rewritten the rules of astrophysics. By the end of this journey, you will see the night sky not as a static picture, but as a dynamic conversation we are only beginning to decode. We will uncover 30 misclassified data blips and dismissed anomalies that forced scientists to rethink dark matter and the fabric of space-time itself. What mysterious pulse from the center of our galaxy was ignored for decades? Why was a signal nearly identical to the famous "wow" message completely forgotten? This exploration reveals how the most profound discoveries often begin as overlooked footnotes in old data archives. How many more universe-altering secrets are still hiding in plain sight, waiting for someone to finally listen? Long before the term pulsar even existed, a young engineer named Jansky was assigned a mundane task: to identify the sources of static hissing on transatlantic radio calls. He built a strange, merry-go-round-like antenna to pinpoint the noise, expecting to find thunderstorms or industrial machinery. Most interference faded away, but one faint, steady hiss remained, and it moved. It traced a slow, deliberate arc across the sky, one that synchronized perfectly with the rotation of the heavens. Jansky had tracked this signal directly to the heart of our own Milky Way galaxy. He was listening to the core of our cosmos for the very first time, yet the official conclusion was terrestrial interference, a notation that buried the finding for decades. The signal's rhythmic nature was the true mystery, a metronomic pulse that modern astronomers instantly recognize. It was the signature of a pulsar, a rapidly spinning neutron star that sweeps the cosmos with beams of radiation like a cosmic lighthouse. But in Jansky's era, the concept of a star behaving like a precise celestial clock was unimaginable. The technology of the time could detect the signal, but the scientific mind was not yet ready to receive its message. This was not a failure of equipment, but a failure of imagination. The universe had sent a clear memo, a ghostly pulse from the galactic center that was dutifully recorded and then completely misunderstood. It serves as a powerful reminder that our most profound discoveries are often not waiting to be found, but waiting to be recognized. That ghostly pulse from the galactic center was a prelude to a much stranger conversation. Decades after Jansky's work, inside a Cambridge lab, a graduate student named Jocelyn Bell-Burnell was staring at miles of paper charts from a new radio telescope. Her eye caught something odd, a bit of scruff that appeared night after night. It was a persistent, rhythmic pulse, so perfectly timed it seemed artificial. She and her advisor jokingly labeled the signal LGM for little green men. The idea that it could be an alien beacon was a genuine, if nervous, consideration. Here was a signal from deep space that behaved with the precision of a master clock, ticking every 1.337 seconds without fail. The scientific establishment was baffled. Nothing in nature was known to be so regular. The signal, catalogued as CP1919, was almost dismissed as terrestrial interference, perhaps from a passing car or a faulty piece of equipment. But its persistence from a fixed point in the sky confirmed its cosmic origin. The truth, when it finally emerged, was far more extraordinary than any fiction. This was not a message from little green men, but the death cry of a star. The signal came from a pulsar, a rapidly spinning neutron star. A neutron star is the unimaginably dense corpse of a massive sun that has exploded. It packs more mass than our own sun into a sphere just a few miles across. A single teaspoon of its material would weigh billions of tons, As it spins, it sweeps beams of intense radiation across the cosmos, and from our viewpoint, we see this as a rhythmic pulse, a lighthouse in the dark. The discovery of that first pulsar was a monumental shift. It taught us a crucial lesson about cosmic communication. The universe does not always speak in languages we expect. Our first instinct was to see a pattern and assume a biological intelligence behind it. Yet the reality was a form of intelligence written in the language of extreme physics, a natural engine of unbelievable power and precision. That forgotten bit of chart recorder scruff redefined the possible endings for a star's life and opened a new window into the most violent and energetic processes in the cosmos. It proved that sometimes the most alien thing we can find is not life, but the sheer, raw physics of existence itself. That first pulsar discovery revealed a universe capable of creating its own perfect clocks. But what happens when the cosmos seems to send a message that is almost, but not quite, perfect? Everyone has heard of the famous wow signal, that shocking 72-second burst of radio noise in 1977, so powerful that the astronomer who found it scribbled wow. In the margin of the data printout, it was a signal that seemed to scream intelligence, arriving from the direction of the constellation Sagittarius, and then vanishing forever. But the true mystery lies in what happened just weeks before. Buried in the same mountain of data was another signal, nearly identical in frequency and originating from the same patch of sky. It was slightly weaker, a quieter whisper that was logged by the equipment and then almost immediately dismissed as a random fluctuation, a mere blip of cosmic static. This signal, the forgotten sibling of the legendary wow, was the universe sending the same calling card twice. The first time we were not listening carefully enough. The second time we were so stunned we could only write a single word in the margin. The existence of this almost wow signal completely changes the story. It suggests the phenomenon might be recurrent, a natural repeating process, or perhaps a beacon that cycles on and off, rather than a single, inexplicable event. By ignoring the first, quieter signal, we created a massive blind spot in our search for cosmic intelligence. Our focus narrowed to that one loud, dramatic anomaly, treating it as a unique mystery to be solved in isolation. We were looking for a shout in the dark while the universe might have been trying to teach us a rhythm. This forgotten sibling forces a more patient approach. It reminds us that the most profound conversations are rarely a single sentence shouted across a room. They are built from repeated phrases, from patterns that emerge only when we are willing to listen for the quiet echoes as intently as we listen for the blast. How many other cosmic messages have we missed because we were waiting for a shout and ignored the whisper that came first? The search for rhythmic patterns in the cosmos can blind us to singular, explosive events. In the early 1980s, a Soviet radio telescope recorded a phenomenon that defied all expectation. A quasar known as QC273, a brilliant beacon at the heart of a distant galaxy, suddenly flared. For one brief moment, it emitted a single, staggering flash of radio energy, a cosmic scream that was never, ever repeated. The observation was largely ignored by the Western scientific community, dismissed as a probable instrumentation error or a glitch in the data. After all, quasars were known to be powerful, but they were also considered relatively steady sources of energy. This one brilliant flash did not fit the established model. It was an anomaly, a ghost in the machine, and so it was quietly forgotten. Yet that solitary flash was a profound clue. It suggested that the violent engines at the hearts of galaxies, the supermassive black holes powering these quasars, are not always stable. The event hinted at a sudden, catastrophic instability in the accretion disk, the swirling whirlpool of superheated gas and dust feeding the black hole. Imagine a log on a fire that does not burn steadily, but instead explodes in a single, brilliant burst of sparks. This is what the forgotten flash of QC273 may have been, a sudden and violent hiccup in the process of cosmic consumption. By dismissing this one-off event, we missed an early opportunity to understand the most volatile and energetic moments in a black hole's life. The universe is not only a place of predictable rhythms, but also of catastrophic, singular outbursts. If we only listen for the ticking of the cosmic clock, we risk being deafened by the occasional explosion. That solitary flash from a distant quasar was a stark reminder of cosmic violence, but the universe also speaks in a constant, quiet murmur. In 1995, a different kind of signal was being recorded, one so subtle and pervasive that it was systematically erased. Across multiple galaxy clusters, astronomers detected a persistent, ultra-low-frequency radio hum. It was not a dramatic pulse or a brilliant flash. It was a drone, a monotone background hiss so uniform that it was considered useless interference. In the quest for clear, sharp data points, this pervasive signal was the first thing to be filtered out. It was the static everyone cleaned from their data, a nuisance to be removed so the real science could begin. The focus of the era was on the hunt for discrete dark matter particles, imagined as singular, elusive entities that could be caught in a detector. No one was looking for a diffuse background hum because the theory did not predict it. This was not a needle in a haystack, it was the haystack itself. We were so focused on finding one specific tree that we failed to notice the entire forest was humming. Today, that forgotten hum is theorized to be something extraordinary, the collective emission from warm dark matter particles weakly interacting with the hot plasma that fills galaxy clusters. It was not noise at all, but the synchronized choir of the universe's most mysterious substance. Each individual particle interaction would be far too faint to detect on its own, but together, across vast cosmic distances, they created a faint, discernible radio whisper. Its dismissal delayed a potential direct detection of dark matter's signature by years, perhaps even decades. The lesson here is profound. We often expect cosmic signals to be distinct events, singular anomalies that stand out from the silence. But sometimes the most important message is not an event at all. It is a new, fundamental layer of reality, a background canvas we have been diligently painting over in our search for clearer pictures. What other fundamental truths are we currently filtering out of our data, simply because we have not yet learned to hear the universe's constant, quiet song? Sometimes the most terrifying cosmic signal comes from a place where nothing should be. In 2001, orbiting detectors recorded a brief, intense burst of gamma rays, the most energetic form of light. The immediate task was to trace its origin, to find the galaxy or exploding star that created it. But when telescopes swiveled to look, they found only a profound emptiness. The burst had come from a cosmic void, a region of space spanning hundreds of millions of light years, largely devoid of any known galaxies, stars, or visible matter. It was a shout from an empty room. The immediate, comfortable conclusion was that it was an instrumental ghost, a glitch in the machine. After all, the established science was clear. Gamma-ray bursts were the birth cries of black holes, the final death screams of massive stars, or the catastrophic collisions of neutron stars. They were supposed to happen in the bustling stellar cities of galaxies, not in the desolate cosmic countryside. This signal did not fit, so it was filed away as a curiosity, a ghost in the data. But this ghost carried a profound message. Its existence challenged a fundamental assumption that immense cosmic violence requires a visible, stellar trigger. The void itself seemed to be the source. This forced scientists to consider truly exotic possibilities. Could the burst have been caused by the final, explosive evaporation of a primordial black hole, a tiny relic from the universe's first second, finally dying in the darkness? Or was it the signature of dark matter particles, annihilating each other in a flash of energy in the depths of that emptiness? The void burst suggests that the cosmic web's emptiest regions are not truly empty at all. They may be filled with the invisible architecture of the universe, a scaffold of dark matter or exotic phenomena we are only beginning to conceive. This forgotten signal teaches us that emptiness is not an absence but a condition. It is a canvas for the universe's most subtle and shocking performances, a reminder that sometimes we must look at the nothing to see the everything. Even the moon, our constant celestial companion, has secrets it has tried to whisper. In the 1960s, during a routine lunar radar experiment, scientists bounced radio waves off the surface to map its topography. The returning echoes painted a picture of the familiar craters and plains, but one echo was different. It returned to Earth not with the expected sharp reply, but with a faint, lingering delay. It was a whisper that lasted mere milliseconds longer than it should have, a subtle anomaly noted as merely curious in a technical report before being filed away and forgotten. That tiny delay was a profound clue. On a world with no atmosphere and a solid surface, a radio wave should bounce back with predictable timing. This delayed echo suggested something hidden. The signal might have slipped into a vast subsurface cavern, echoing in the darkness before finding its way back out. Alternatively, it could have been slowed by passing through a deep layer of an unusual material, something with properties that defied the known composition of lunar rock. In that fleeting millisecond was the potential map to a subterranean world. Its dismissal was a lost opportunity of staggering proportions. We had a chance, decades ago, to begin probing the moon's hidden architecture, to know if vast, stable caverns lay beneath the dust, perfect natural shelters from cosmic radiation and temperature extremes. Today, the search for such subsurface structures is a primary goal for lunar colonization, a key to establishing a permanent human presence. We are now building the tools to listen for that whisper again, a whisper we first heard over half a century ago and chose to ignore. It stands as a quiet testament that mystery is not always found in the depths of distant space. Sometimes it is waiting for us in the silent shadows of our own sky. Deep beneath the Earth, shielded from the sun's blinding light, a different kind of ear was listening to our star. In the 1970s, a pioneering underground detector was built to catch neutrinos, the ghostly subatomic particles that stream directly from the sun's core. For the first time, we had a window into the very engine of our solar system. The data flowed steadily, a quiet confirmation of our theories about nuclear fusion. Then something impossible happened. The signal from the sun suddenly dropped. The number of neutrinos arriving at our planet fell by almost half, a staggering decrease that lasted for a brief period before mysteriously returning to normal. The immediate, logical conclusion was a temporary equipment fault. A wire must have come loose, a sensor must have failed. It was far easier to blame our own flawed machinery than to suggest the sun itself had momentarily faltered. This neutrino dropout event was logged as an anomaly and promptly forgotten, a ghost in the basement. Yet that fleeting drop was a message from the heart of the sun, a truth we were not ready to hear. The neutrinos were not disappearing, they were changing. On their 8-minute journey to Earth, these chameleon-like particles were oscillating, shifting between 3 different identities or flavors. Our detector was only built to catch one specific flavor. For that brief period, a larger fraction of the Sun's neutrinos had simply changed their disguise, becoming invisible to our one-eyed gaze. By dismissing this fluctuation, we delayed a fundamental revelation for decades. Neutrinos, long thought to be massless phantoms, had to have a tiny amount of mass to undergo this transformation. That forgotten 50% drop was a direct challenge to the standard model of particle physics, our most complete theory of the universe's building blocks. We had to rewrite the rules because the Sun tried to tell us something was wrong with our textbook. It is a humbling lesson in scientific humility. We built a perfect machine to confirm a perfect theory, and when the universe sent back an imperfect answer, we assumed the machine was broken. Sometimes the most profound truth is not in the steady signal, but in the moment it quietly vanishes. That fleeting drop in solar neutrinos was a ghost in our own basement, a signal from the Sun we refused to believe. But sometimes the ghosts are not in our machines, but in our old filing cabinets. Decades before the term fast radio burst entered the astronomical lexicon, a Canadian astronomer was sifting through reams of data in the late 1980s. His logbook contains a single, curious entry, a note on a strange, dispersed pulse. The signal had a unique fingerprint, a characteristic sweep across different radio frequencies. Higher frequencies arrived a fraction of a second before the lower ones, a clear sign that this burst had traveled a vast cosmic distance, its waves stretched and delayed by the thin gas of intergalactic space. This was the unmistakable signature of a fast radio burst, yet the official designation was simple and dismissive: unidentified radio frequency interference. It was a ghost, and so it was filed away. That single, forgotten data point is a revelation. It proves that these incredibly powerful, millisecond-long cosmic explosions are not a new phenomenon of the modern universe. They were not suddenly switching on. They had been flashing in the darkness for decades, perhaps for centuries, their messages arriving at our doorstep only to be turned away by our own assumptions. We were not listening for them, so we called their knocks at our door mere interference. The existence of this 1989 precursor completely rewrites the timeline. If these events were happening then, and we are only now building telescopes sensitive enough to find them regularly, it means the true rate of these bursts could be far, far higher than our current models suggest. Every model for what creates these titanic explosions, from colliding neutron stars to the violent eruptions of magnetars, is built on how often we think they occur. This one forgotten signal suggests the cosmos might be a much more violent and explosive neighborhood than we ever calculated. The universe was trying to send us a message about its most cataclysmic engines, and we wrote it off as a glitch. It forces a humbling question: how many other cosmic secrets are sitting in plain sight, waiting in dusty archives for a new generation to finally understand what they are hearing? That forgotten 1989 data point proved we were ignoring cosmic explosions for decades. But sometimes the most telling signal is not a violent flash, but a quiet contradiction in a familiar face. In 1992, a detailed radio survey mapped the hydrogen gas of a seemingly ordinary spiral galaxy, a pinwheel of stars much like our own Milky Way. The data painted a beautiful, rotating disk, but it also contained a ghost, a faint and separate disk of hydrogen gas spinning in the exact opposite direction. This counter-rotating disk was so bizarre, so fundamentally strange, that the team assumed it was a data processing artifact, a glitch in their software. The finding was never published, dismissed as a ghost in the machine. Yet this forgotten signal was a fossil record of galactic violence. That faint, backward-spinning disk was the ghost of a smaller galaxy that had been captured and torn apart. Billions of years ago, this victim galaxy had fallen in on a retrograde orbit, a cosmic wrong-way driver, and was shredded by gravitational tides. Its stars and gas were absorbed, but the memory of its original motion was preserved in that stubborn, counter-rotating hydrogen. It was a clear case of galactic cannibalism, a meal whose aftermath was still visible. By ignoring this signal, we missed a masterclass in galactic evolution. This hidden dynamic is not just a curiosity. A galaxy that consumes another in this way has its entire life story rewritten. The collision of these two rotating disks of gas creates immense shock waves and turbulence, triggering furious bursts of new star formation and funneling material toward the central supermassive black hole, potentially awakening it as a brilliant quasar. The galaxy's lifespan, its future growth, and the very lives of its stars are all shaped by this single, forgotten event. That faint signal whispers a crucial truth. The most familiar objects in our sky, the serene spiral galaxies we sketch in textbooks, are not always born serene. They are the products of ancient violence, cosmic predators that have absorbed their neighbors. Their beautiful symmetry can hide a deeply turbulent past, a history written not in light, but in the subtle, opposing motions of invisible gas. That faint, backward-spinning galaxy was a fossil of ancient violence, but another ghost was hiding in the very afterglow of creation itself. Years before the Planck satellite would make it famous, a high-altitude balloon experiment drifting in the thin air above Antarctica recorded a puzzling map of the cosmic microwave background, the faint echo of the Big Bang. In that map was a region of sky, vast and profoundly cold, a patch of shadow in the primordial light. The data was clear, but the interpretation was not. The anomaly was deemed statistically marginal, a probable fluke in the noise, and so it was relegated to a footnote in a long technical report. It was too strange, too large, and too threatening to the pristine model of a uniform early universe to be taken seriously. This was the cold spot, a cosmic bruise that should not exist. Its initial dismissal was a classic example of scientific conservatism. When an anomaly directly challenges a foundational pillar of our understanding, the first instinct is often to assume the data is wrong, not the theory. The standard model of cosmic inflation painted a picture of a remarkably smooth and homogeneous early universe. A cold spot this large was like finding a frozen continent on a map that was supposed to show a warm, global ocean. It simply did not belong, but the cold spot refused to go away. As more sensitive instruments confirmed its existence, the explanations became increasingly radical. One terrifying possibility is that this spot is a cosmic scar, the imprint of a collision with a bubble universe from the multiverse. In this scenario, our entire cosmos is one expanding bubble in a frothing sea of other realities, and the cold spot is where we once brushed against another, entirely different universe. The alternative is scarcely less dramatic, that the spot is a sign of a gargantuan void, a cosmic supervoid so immense that its gravitational pull has drained energy from the light passing through it, leaving a cold shadow on the ancient sky. Both ideas force a confrontation with our most basic assumptions. The cold spot's journey from a dismissed footnote to a central cosmological mystery reveals a profound truth about how science grapples with the unknown. We build elegant models to describe the cosmos, but the universe has a habit of leaving messy fingerprints on our blueprints. This forgotten cold patch is more than just a statistical anomaly. It is a potential doorway to a reality far grander and more bizarre than we ever imagined. A reminder that the greatest discoveries are often the ones that make us most uncomfortable. Even the most perfect cosmic clocks can sometimes skip a beat. In the 1990s, astronomers discovered a pulsar of such incredible stability, it was nicknamed the Diamond Pulsar. a celestial metronome whose rhythmic pulses were more precise than any atomic clock on Earth. Its steady tick was a marvel of nature, a testament to the predictable physics of a spinning neutron star, yet hidden within its brilliant signal was a strange and subtle flaw. When researchers analyzed its full spectrum of radio emissions, they noticed that one of its harmonic frequencies was simply not there. It was a gap in the music, a silent note in the pulsar's otherwise perfect song. This missing harmonic was not a dramatic event but a quiet absence. The immediate, logical conclusion was an observational glitch. Perhaps a filter in the receiver had malfunctioned, or a burst of terrestrial static had momentarily masked that specific frequency. It was a small detail in a vast dataset, an anomaly easily dismissed as a problem with the equipment rather than a message from the star itself. That decision to ignore the silent note cost us a profound insight. We now understand that such a missing harmonic is not a glitch, but a fingerprint. The complex interior of a neutron star is a realm of almost unimaginable physics, where matter is crushed into states that do not exist anywhere else. The gap in the signal can be the signature of a superfluid core, a bizarre quantum liquid that flows without any friction whatsoever. As the star's solid crust rotates, this internal ocean of superfluid may slosh in a way that cancels out one specific vibrational frequency, effectively silencing it. Alternatively, the star's immensely powerful magnetic field, trillions of times stronger than Earth's, could be configured in a way that traps or absorbs radiation at that one precise wavelength. In either case, the absence of the harmonic is a direct window into the star's quantum heart. By dismissing it as a simple error, we missed an early and crucial clue. We had a chance to peer directly into the exotic states of matter that form under pressures so extreme that atoms themselves are destroyed, leaving behind a soup of subatomic particles governed by the strange rules of quantum mechanics. That forgotten frequency is a powerful lesson in cosmic listening. We are often trained to hunt for signals for the things that are present in our data. But the universe communicates just as eloquently through its silences. The empty spaces in a spectrum, the quiet gaps in the noise, these are not merely voids. They are the echoes of structures and forces too strange for our everyday intuition, waiting for us to recognize that sometimes nothing is the most important something of all. That silent gap in the pulsar's song taught us to listen for the universe's quiet absences, but sometimes a whisper arrives in the wake of a cosmic roar. When the LIGO Observatory made its first historic detection of gravitational waves in 2015, the world celebrated a triumph. We had finally heard the faint ripple in spacetime from two black holes colliding a billion light-years away. The main signal, a rising chirp that ended in a final, smooth ringdown, was a perfect match for Einstein's predictions. But in the raw data, just milliseconds after that final ringdown faded, there was something else. A faint, repeating echo. It was a subtle series of bumps, a quiet reverberation that seemed to bounce back from the very edge of the newly formed black hole. In the overwhelming excitement of confirming a century-old theory, this echo was deemed too statistically weak to claim. It was labeled as post-processing noise and removed from the official discovery paper. The gravitational wave echo was a ghost sacrificed for the sake of a clean, monumental story. Yet that faint reverberation, if it was real, carries implications far beyond the merger itself. The standard model of a black hole, defined by its event horizon, predicts a clean ending. Anything that crosses that boundary is gone forever, leaving behind only a smooth, featureless void. An echo, however, suggests a barrier. It hints that the event horizon might not be a one-way street into nothingness, but a physical structure, a quantum firewall or a fuzzball of strings that can briefly trap and reflect gravitational energy. This echo could be the first experimental signature of quantum gravity, a fleeting glimpse of the physics that governs the universe at its most fundamental scale. Its dismissal reveals a profound tension in how we do science. In the hunt for a clear, confirmatory discovery, we are often forced to clean our data of ambiguity. We prioritize the signal we understand over the noise we do not, but the universe is under no obligation to be unambiguous. That forgotten echo suggests that the most revolutionary truths are not always in the loud, triumphant shout, but in the faint, messy whispers that follow, the ones we are most tempted to erase in our quest for a perfect picture. A single particle once fell to Earth carrying more energy than any human-built accelerator could ever produce. In the 1980s, a cosmic ray detector recorded the arrival of one such particle, an atomic nucleus moving at nearly the speed of light. Its energy was so immense it broke a fundamental rule of astrophysics, the GZK limit. This theoretical ceiling states that particles with such high energy should be destroyed over long distances, scattered by the faint glow of the cosmic microwave background before they can ever reach us. This particle should not have existed, and its origin was just as baffling. It came from the galactic plane, the crowded disk of our own Milky Way, a region devoid of any known object powerful enough to be its source. There were no supernova remnants, no active black holes, nothing that could serve as a cosmic cannon of such unbelievable force. The official response was to label it an anomalous outlier, a statistical ghost that was deliberately purged from major catalogs to keep the data clean. Its existence was an inconvenience, a single data point that threatened to unravel our entire understanding of high-energy physics. By removing it, we created a comforting but deeply flawed map of the universe's most energetic phenomena. We assumed the most powerful particle accelerators were in distant, active galaxies, and we filtered out any evidence that suggested they might be hiding in our own cosmic backyard. This forgotten particle was a clue to something monstrous lurking in the familiar sprawl of the Milky Way, a silent engine capable of feats we thought were impossible. Its dismissal taught us a dangerous lesson, that when we clean our data of outliers, we might be erasing the very signatures that point to a new frontier of physics. A supernova's light should tell a perfect story of cosmic expansion. In the 1930s, as astronomers tracked the brilliant death of a star in a distant galaxy, a junior researcher noticed a subtle flaw in the narrative. The starlight was dimming slightly more than its redshift implied it should. According to the prevailing theory of an expanding universe, the light's color shift, its redshift, indicated how fast the galaxy was receding and thus its distance. That distance, in turn, predicted how bright the supernova should appear, yet this one was just a little too faint. The senior astronomers had a ready explanation: atmospheric extinction. They concluded that ordinary earthly haze, a bit of fog or pollution in our own atmosphere, was responsible for the extra dimming. The junior astronomer's careful notation was set aside, a minor discrepancy buried in a logbook. This was the forgotten tired light signature. The name itself comes from a long disproven alternative to the Big Bang, a static universe where light simply gets tired and loses energy over vast distances. While that particular theory was wrong, the observed effect was real. That supernova's light was not tired, but it was being obscured. It was fighting its way through a cosmic fog, a thin mist of microscopic dust grains scattered between the stars and between the galaxies. Each tiny particle absorbed a little starlight, dimming the supernova just enough to create that puzzling anomaly. By dismissing this signal, we chose a simpler, cleaner universe, one where light traveled unimpeded. We failed to see the haze. For decades, this oversight meant our cosmic distance ladder was built on a flawed assumption of perfect clarity. We thought we were measuring the universe through pristine air, when in fact we were looking through a dirty window. The consequence was a miscalibration of cosmic scales. When we finally rediscovered this effect, it forced a profound revision. The universe was not only expanding, it was dusty. This cosmic fog is now a critical correction in modern cosmology, especially for measurements that probe the nature of dark energy. That forgotten dimming from a 1930s supernova was the universe trying to teach us a crucial lesson about our own imperfect vision. It reminds us that to see the cosmos clearly, we must first learn to account for the dust on the lens. Even the giant planet Jupiter could not drown out the faint cry of its most tortured moon. Years before any spacecraft visited the outer solar system, radio astronomers listening to Jupiter's own powerful bursts of static occasionally noted a faint, low-level hiss that seemed to shift with the orbital position of its moon Io. It was a subtle background noise, easily overwhelmed by the king of planets' own roaring magnetospheric emissions. The logical conclusion was simple interference, a faint echo of Jupiter's own voice. It was a ghost in the static, and so it was filtered out, a nuisance signal to be removed for a clearer picture of the primary target. That faint, forgotten hiss was not an echo at all. It was a scream. It was the direct radio signature of a cosmic electrical circuit of staggering scale. Jupiter's immense magnetic field sweeps past Io, and in doing so, it acts like a gigantic generator, ripping charged particles from the moon's thin atmosphere and funneling them along magnetic field lines. This creates a permanent, donut-shaped ring of superheated plasma, a charged gas that orbits Jupiter, locked in place by Io's gravity. That radio hiss was the sound of this plasma torus itself, the hum of a billion-amp current flowing between a moon and its planet. By dismissing this signal, we missed an early prediction of a world on fire. We had the data pointing to a geological inferno decades before the Voyager probes sent back the first stunning images of Io's erupting volcanoes. The hiss was the direct consequence of that volcanism, as sulfur dioxide volcanoes constantly replenish the atmosphere that Jupiter's magnetic field is relentlessly stripping away. We were listening to the real-time destruction and renewal of a world, and we called it noise. It stands as a stark lesson in cosmic context. We were so focused on understanding the powerful, obvious signal from the giant planet that we tuned out the desperate whisper from its small companion, a whisper that held the key to the most volcanically active body in our entire solar system. It begs a sobering question: what other planetary dramas are we missing right now, simply because we are not listening carefully enough to the quietest voices in the chorus? A supermassive black hole's feast should be a steady, monstrous glow. Yet in the early 1970s, an X-ray telescope pointed at a nearby active galaxy recorded something strange. The brilliant beacon at its heart, the active galactic nucleus, was not shining with a constant fury. It was flickering. Its X-ray output wavered with tiny, rapid fluctuations, brightening and dimming again in a matter of minutes. The signal was faint, like a distant candle flame guttering in a cosmic wind, but it was unmistakably there. For the scientists reviewing the data, this was not a discovery, it was an impossibility. The physics of the time dictated that an accretion disk, the swirling whirlpool of matter feeding a black hole millions of times the mass of our Sun, was simply too large and too slow to change on such a rapid timescale. The entire structure was light days or even light weeks across. A change in brightness that happened in minutes would require the entire disk to brighten or dim in near-perfect unison, a coordination that seemed physically absurd. The only logical conclusion was a faulty detector, a random electronic sputter in their own machinery. The flicker was labeled an artifact and systematically erased from the official analysis, a ghost sacrificed for the sake of a sensible model. This dismissal cost us an early glimpse into the final fall. Those rapid flickers were not a glitch, they were a strobe light illuminating the very edge of oblivion. The timescale of a flicker is a direct measure of size. If something brightens and dims in a few minutes, the source of that variation cannot be larger than the distance light can travel in those few minutes. Otherwise, the change would be smeared out like a crowd cheering out of sync. Those minute-long flickers placed the origin of the X-rays in a terrifyingly small region, a space just a few times larger than the black hole's event horizon itself. We were not seeing the entire accretion disk change. We were witnessing individual clumps of superheated gas, final desperate comets of matter, screaming in X-rays as they made their last frantic orbits before plunging past the point of no return. Each flicker was a timestamp from the brink, a direct probe of space and time twisted into a vicious not by gravity itself. By ignoring this signal, we delayed the birth of an entire field of science, X-ray timing. We had a tool that could directly measure the orbit of material deep within the gravitational grip of a supermassive black hole, and we threw it away because the answer it gave us seemed too fantastic to be true. Today, we actively hunt for these precise flickers. They are our most powerful stopwatch for testing Einstein's theory of general relativity in its most extreme regime. The rhythm of those flashes can reveal the spin of the black hole, the stability of the innermost stable orbit, and the very nature of spacetime as it is stretched to its breaking point. That forgotten flicker from the 1970s was a key offered to us, a key to the inner sanctum of a cosmic monster. We looked at it, decided it was the wrong shape, and tossed it aside for a generation. It is a stark lesson in the danger of a universe that behaves too perfectly. When our models are too clean, the messy, flickering truth can become invisible. A brilliant flash of light appeared on a glass photographic plate in 1956, a single bright point where none had been before. Astronomers catalogued it as a probable variable star, a sun whose brightness naturally waxed and waned, and then they moved on. The event was an orphan, a burst of visible light with no parent. It had no accompanying signal in gamma rays, the most powerful form of energy, which meant it defied the very definition of a cosmic explosion. It was a solitary witness to an event that, according to all our theories, should not have been visible at all. This orphan was a cosmic message sent from the wrong address. We now understand this forgotten flash was the visible light echo of a gamma-ray burst, one of the most violent explosions in the universe since the Big Bang. But there was a twist. The gamma-ray burst itself was invisible to us because its high-energy beam was not pointed at Earth. Imagine a lighthouse in a distant ocean, its powerful lamp spinning in the darkness. If you are not directly in the beam, you see only a dim glow reflecting off the surrounding clouds and fog. That is what we recorded in 1956. We were not in the main beam of the cosmic lighthouse, but we saw the illuminated aftermath, the visible light shining from the heated gas and dust around the explosion. This orphan afterglow was crucial evidence that gamma-ray bursts are not simple, spherical explosions. They are focused, directional events, firing twin jets of intense radiation from their poles like a titanic cosmic rifle. By forgetting this signal, by miscataloguing it as a simple variable star, we made a critical error in our census of the cosmos. We assumed that every gamma-ray burst that occurred would send its main beam our way, allowing us to see it. We were only counting the ones that happened to be aimed directly at our planet. The existence of the orphan afterglow proves that for every one we see, there are hundreds, perhaps thousands, pointed in other directions, flashing in the darkness completely unnoticed. For decades, this meant we drastically underestimated the true, terrifying frequency of these stellar cataclysms. Our entire understanding of their role as cosmic yardsticks, as tools to measure the expansion of the universe, was built on a flawed, incomplete sample. We thought we were taking a full head count of the universe's most violent events, but we were only seeing those rare few that happened to look us directly in the eye. How many other cosmic explosions have we missed simply because we were standing in the wrong place to see the main show? The universe can hide entire worlds in the light we choose to ignore. A star catalogued in the early days of infrared astronomy seemed perfectly ordinary, its visible light steady and calm. But for a brief period, its infrared glow, the heat signature of the star, took a mysterious and isolated dip. This was not a dimming across all colors of light, only in the specific, longer wavelengths that our eyes cannot see. The immediate assumption was a faulty sensor. Infrared technology was new and notoriously finicky, susceptible to temperature fluctuations and electronic ghosts. The simplest explanation was that the instrument itself had blinked, registering a shadow that was not really there. This unexplained dip was filed away as a technical glitch, another ghost in the nascent machine of a new science. That decision to dismiss the anomaly cost us an early glimpse into a stellar nursery. The signal was a perfect fingerprint of a circumstellar debris disk, a vast cold ring of dust and rock orbiting the star at a great distance. The reason the dimming occurred only in the infrared is a matter of simple physics. Visible light, with its shorter wavelengths, could pass through this tenuous cloud of material largely unaffected. But the longer wavelengths of infrared light, which correspond to heat, were being partially blocked and absorbed by the countless trillions of cold, dusty particles in the disk. It was like a fine mist that is invisible to the naked eye, but which you can feel as a distinct chill on your skin. That single, forgotten dip was the thermal shadow of a construction zone, a place where planetesimals were colliding and coalescing in the dark, cold depths far from the central star's heat. By ignoring it, we delayed the understanding that our solar system is not unique. We missed a crucial piece of evidence that the raw materials for planets, the vast reservoirs of ice and rock that eventually clump together into worlds, are a common feature around young stars. For years, we searched for other planetary systems by looking for the wobble of a star or the transit of a giant planet, methods that find the finished products. That infrared whisper was trying to show us the lumberyards and quarries, the source of the materials themselves. It asks a profound question of us now. How many other cradles of creation have we already seen and dismissed, simply because we trusted our machines more than the subtle story the light was trying to tell? A ghost of pure potential drifted through the cosmos, a vast, spinning cloud of hydrogen gas with no stars to give it form. In the 1980s, radio telescopes mapped this immense structure, a celestial whirlpool of pristine fuel stretching across thousands of light years. It was rotating with the clear, organized motion of a galaxy, yet it was completely, utterly dark. No pinpricks of light shone within it. No stellar nurseries glowed in its depths. The official explanation was one of cosmic destruction, not creation. Astronomers concluded it was a tidal tail, a mere streamer of gas ripped away during a violent collision between two brighter galaxies. It was not a thing itself, but the debris of other things, a ghost story written in hydrogen and promptly forgotten. This dismissal was a classic case of seeing what we expected to see. Our definition of a galaxy was inextricably linked to stars. A thing that had no stars, by that logic, could not be a galaxy. It was a collection of parts without a whole, a cosmic cloud that had failed to awaken. By labeling it debris, we hid a profound truth about the universe's quiet failures. This dark cloud, a candidate for a dark galaxy, was a crucial piece of the cosmic puzzle. It was a galaxy that never truly lit up, a system where the raw materials for suns were present in abundance, but the spark of star formation never caught. Its existence challenges our most fundamental models of galaxy birth. Why do some clouds of gas collapse into brilliant pinwheels of stars, while others like this one simply drift cold and dark for billions of years? The answer lies in the invisible scaffold of dark matter. A successful galaxy is thought to be anchored by a massive, dense halo of dark matter, whose gravity pulls in gas and triggers the birth of stars. This dark galaxy candidate suggests a different story, one of a halo that is too diffuse, too weak to compress the gas sufficiently. It is a galaxy that failed to ignite. Its reclassification as mere debris hid an entire population of these ghostly islands, now known as ultra-diffuse galaxies. These faint, sprawling systems are crucial testing grounds for dark matter theories. If our models are correct, they should be held together by incredibly dense, compact cores of dark matter, preventing them from being torn apart by the gravity of their larger neighbors. Finding and studying these dark, forgotten clouds allows us to probe the distribution and behavior of dark matter in a way that bright galaxies simply cannot. That single, starless spin of hydrogen was not debris, it was a question. It asked us to reconsider what makes a galaxy and to listen for the stories of the ones that never learned to sing. Even our own sun holds back secrets about its own breath. In the early 1970s, a pioneering spacecraft was stationed to monitor the solar wind, that constant stream of charged particles flowing from the sun and washing over the entire solar system. Its instruments were calibrated to measure the wind's basic composition, primarily the ratio of hydrogen, the lightest element, to helium, the next most abundant. For the most part, the readings were steady, a predictable mix that matched our understanding of the sun's interior. Then, for one brief period, the ratio shifted dramatically. The percentage of helium spiked in a way that made no sense. The official verdict was swift and sensible: a sensor calibration error. A temporary glitch in the machine had skewed the numbers, creating a ghost in the data that was promptly filtered out and forgotten. This dismissal was a classic case of trusting our expectations over the evidence. We assumed the sun's atmosphere was a well-mixed soup, expelling a uniform wind from all its regions. That anomalous helium reading, however, was a true signal, the fingerprint of a specific kind of solar storm known as a coronal mass ejection. These are billion-ton clouds of solar plasma hurled into space, but they do not all come from the same place. The sun's corona, its outer atmosphere, is not a uniform shell. It is a patchwork of magnetic domains, some open to space and some closed in loops. The anomaly occurred when the spacecraft was hit by material ejected from a magnetically complex region where the sun's processes can selectively concentrate heavier elements like helium before blasting them outward. It was a sample from a specific solar factory, not from the general population. By ignoring this signal, we clung to a simpler, smoother model of our star for years. We delayed the realization that the solar wind is not one wind, but many. It is a collection of distinct streams, each with its own unique composition and speed, originating from different magnetic landscapes on the sun's surface. That forgotten data point was a crucial early clue to the segmented and dynamic nature of the sun's outer atmosphere. It reveals that even our closest star speaks in different dialects, and for a brief moment, we recorded a whisper in a language we did not yet understand. A faint statistical blip appeared in a neutrino detector, a slight excess of ghostly particles from a seemingly empty patch of sky. With the poor angular resolution of the time, the signal was too diffuse to pinpoint a source. It was written off as a meaningless background fluctuation, a random clustering in the noise that held no real significance. This was the forgotten neutrino glow of the Geminga pulsar, a whisper from one of the most powerful natural engines in our galactic neighborhood. We had recorded a direct signal from its heart, and we called it a ghost. The dismissal of that faint excess created a major roadblock in a century-long cosmic mystery. For decades, we have known that Earth is constantly bombarded by high-energy cosmic rays, atomic nuclei traveling at nearly the speed of light, but their origins have been incredibly difficult to trace. Because these particles carry an electric charge, their paths are bent and scrambled by the magnetic fields that fill the galaxy. By the time they reach us, they are like letters delivered to our doorstep with the return address completely smudged by rain. We knew the mail was arriving, but we had no idea who was sending it. That faint neutrino glow was a clean, unsmudged return address. Neutrinos, unlike cosmic rays, are neutral particles. They do not interact with magnetic fields. They travel in perfectly straight lines from their source, untouched and undeflected, carrying a direct message about where they were born. The excess from Geminga's direction was a telegram from a cosmic ray factory. It was telling us that right there, in that specific spinning stellar corpse, protons and other atomic nuclei were being accelerated to unbelievable speeds in the intense magnetic and electric fields surrounding the pulsar. These particles were being whipped to nearly the speed of light and then blasted out into the galaxy, some of them eventually finding their way to Earth. By ignoring the neutrino clue, we delayed the crucial link between a specific, identifiable celestial object and the rain of high-energy particles that has puzzled us for over 100 years. We were so focused on the scrambled cosmic rays that we ignored the pristine neutrino messenger that arrived at the same time, pointing directly back to the source. It forces us to wonder how many other cosmic ray factories are currently flooding our detectors with neutrinos, their clean, straight-line messages being dismissed as mere statistical noise. Radar screens in the 1950s were meant to track incoming meteors, not stationary ghosts in the sky. Yet one station recorded a persistent series of echoes that defied explanation. They appeared high above the atmosphere, and they repeated with a perfect 24-hour rhythm, a daily celestial check-in that was as predictable as the sunrise. The official conclusion was simple ground clutter. It had to be a reflection from a nearby hill or a building, some terrestrial object fooling the system into seeing something that was not there. The echoes were duly logged as unexplained but probably terrestrial, and then they were forgotten. That decision hid a secret structure in our own cosmic backyard. We now suspect those forgotten echoes were not bouncing off hills, but off a vast, stable cloud of dust particles trapped at a gravitational parking spot known as the Earth-Sun L1 Lagrange point. This is a place in space where the gravitational pull of our planet and the Sun perfectly balance, creating a point of equilibrium. In this stable zone, fine interplanetary dust can accumulate, held in a loose, shimmering cloud that perpetually leads Earth in its orbit around the Sun. For decades, we were unaware of this potential reservoir of ancient material, a silent, dusty companion traveling with us through the solar system. Its dismissal meant we overlooked a key feature of our local space environment. This cloud could be a library of the solar system's earliest building blocks, pristine samples of the dust from which the planets formed, held in suspended animation just 1 million miles away. By labeling the radar return as mere ground clutter, we turned away from a nearby cosmic mystery, a reminder that sometimes the most intriguing signals are not from the depths of the universe, but from the quiet, gravitational eddies just ahead of us in our own orbital path. A star's light can be a fossil record of the universe's first moments. In the 1990s, astronomers turned their spectrographs toward one of the oldest stars ever found, a relic from the cosmic dawn that was almost entirely devoid of heavy elements. By splitting its light into a rainbow, they could read its chemical composition like a historical document. The levels of hydrogen and helium matched predictions perfectly, but one element was out of place. The amount of lithium, the third lightest element, was significantly lower than the established models of Big Bang nucleosynthesis said it should be. This was not a dramatic anomaly, just a quiet deficit. The official explanation was a comfortable one, an incomplete stellar model. They concluded that their understanding of the star's own atmosphere was flawed, that processes within the ancient star itself must have consumed some of the lithium over billions of years, creating a misleading reading. The discrepancy was filed away as a technical problem, a ghost in the theory. This dismissal was a choice to ignore a crack in the foundation of our cosmic origin story. The models of Big Bang nucleosynthesis are one of the three great pillars supporting our entire picture of the universe's birth, alongside the cosmic microwave background and the redshift of galaxies. That lithium measurement was not an error, it was a direct empirical test of what happened in the first 20 minutes of existence. The fact that the prediction and the observation did not match meant that something was fundamentally wrong. Either our understanding of the nuclear physics in the primordial universe is incomplete, requiring new, exotic particles or forces to explain the discrepancy, or our theories about how the first stars lived and burned are utterly mistaken. By attributing the signal to a modeling error, we delayed a necessary crisis. We preferred a universe that conformed to our elegant equations, rather than confronting the messy reality that the data was presenting. This forgotten lithium deficit has since blossomed into a major unsolved problem in cosmology. It is a small, quiet number that threatens to rewrite the first chapter of everything, a reminder that sometimes the most universe-altering secrets are not written in brilliant flashes of light, but in the faint, missing lines of an ancient star's chemical signature. Our own planet's atmosphere can sometimes catch a cosmic bullet. While the Vela satellites silently watched for the telltale double flash of a nuclear detonation, their sensitive eyes occasionally recorded a different kind of event. These were uncorrelated flashes, bursts of light with no accompanying thunder of an explosion on Earth and no map to a lightning storm below. They were ghosts in the machine, isolated incidents that did not fit the profile of a bomb or any known natural phenomenon. The official protocol was simple and secretive: archive and move on. These anomalies were buried in classified logs, their true nature locked away behind layers of national security. For years, these events were the ultimate forgotten signals, dismissed not because of a lack of curiosity, but because their very existence was a state secret. The truth, when it finally emerged, was almost as shocking as a nuclear blast. These uncorrelated flashes are now believed to be the fingerprints of something called a terrestrial gamma-ray flash. Imagine a lightning strike in reverse, firing not down to the ground but powerfully upward, out of the top of a thunderstorm and into the near vacuum of space. This colossal discharge of electricity acts like a natural particle accelerator, whipping electrons to incredible speeds and producing a brief, intense burst of gamma radiation, the most energetic form of light in the universe. The Vela satellites, designed to watch for human-made Armageddon, were instead witnessing a previously unknown form of atmospheric Armageddon, a natural weapon of immense power firing from our own world into the cosmos. Their secretive classification created a perfect storm of forgetting. The data was not accessible to the astrophysicists who could have interpreted it, and the military analysts who did see it had no reason to connect these flashes to cosmic phenomena. This kept an entire branch of high-energy atmospheric physics hidden in plain sight for decades. We were so focused on the weapons we could build that we missed the ones the sky was building for itself. It is a stark lesson in how the walls we build for security can also become walls that block our view of the universe, leaving us oblivious to the spectacular violence happening right over our heads. A single star in a 19th century catalogue refused to stay perfectly still. While its celestial neighbors appeared fixed in their positions, this one sun displayed a tiny, almost imperceptible drift against the backdrop of the cosmos. The astronomers of the day, relying on manual measurements with micrometers and glass plates, noted the discrepancy, but their conclusion was one of human error, not cosmic truth. They assumed the anomaly was a mistake in the arduous, eye-straining process of charting the heavens, a flaw in the observer rather than a feature of the star itself. This minuscule motion was a whisper of proximity or a hidden dance. We now understand that a star's proper motion, its apparent drift across our sky, is a direct indicator of its distance from us and the gravitational company it keeps. The stars that seem to move the fastest are typically the closest ones, just as a nearby tree seems to speed past a train window while distant mountains appear almost stationary. That forgotten star with its anomalous drift was likely one of our close stellar neighbors, a red dwarf too faint to be notable in visible light, yet lurking remarkably near to our solar system. Alternatively, that tiny wobble in its path could have been the gravitational signature of a massive, unseen companion, a dark stellar corpse like a neutron star or even a black hole, tugging on its visible partner as they circled one another in the dark. By dismissing this signal, we turned away from a map of our local cosmic neighborhood. We failed to see the subtle dynamics playing out in our own stellar backyard, all because the evidence was a quiet, inconvenient detail that did not fit the era's technological and conceptual limits. It is a profound lesson in the importance of the smallest data point. The universe's grandest secrets are not always announced with brilliant flashes or roaring bursts. Sometimes they are encoded in a single star's quiet, stubborn refusal to remain exactly where we thought it should be. A quasar's light is a cosmic probe, traveling across billions of light years and passing through every cloud and filament of matter in its path. In the early 2000s, astronomers recorded the spectrum of one such brilliant beacon, splitting its light into a rainbow to read the chemical fingerprints of everything it had encountered. The data revealed a curious, quiet absence, a specific absorption line, a telltale dip in the spectrum that should have been strong according to their models, was surprisingly faint. It was a missing piece of the story, a gap in the narrative that was noted in the paper as a minor curiosity before the research moved on to more prominent conclusions. This was not a dramatic anomaly, but a whisper of something vast and invisible. That weak absorption line was the ghostly signature of the warm-hot intergalactic medium, often called the WIM. This is not a cold, dense gas, but a superheated, incredibly diffuse fog of plasma that exists in the filaments of the cosmic web, the grand scaffolding upon which galaxies are arranged. For decades, a huge portion of the universe's normal matter, the ordinary atoms that make up stars, planets, and us, was completely unaccounted for. Our inventories of cosmic matter never added up. The missing baryons were not in the galaxies, they were in the spaces between them, hiding in this thin, seething ocean of gas. By dismissing that faint spectral line, we delayed the mapping of this final reservoir. We were looking for the water in the rivers and lakes while ignoring the humidity in the air itself. The signal was trying to tell us that the empty spaces between galaxies are not empty at all. They are filled with a tenuous but immensely important sea of normal matter, a web of gas so hot it is invisible to most telescopes and so diffuse that a cubic meter of it might contain only a few atoms. Its detection is one of the great triumphs of modern cosmology, yet its first whisper was heard years earlier and quietly set aside. How many other fundamental components of reality are we still ignoring because their signal is a quiet absence in our data rather than a brilliant flash? A faint star that was not quite a star sent out a rhythmic call. In the mid-1990s, a radio survey picked up sporadic, highly polarized bursts from a dim, cool object known as a brown dwarf. These were not the steady ticks of a pulsar, but sharp, unpredictable crackles of energy. The signal was polarized, meaning its radio waves were all aligned in a single direction, a classic fingerprint of a coherent source generated by a powerful magnetic field. Yet the official conclusion was terrestrial interference. The reasoning seemed sound at the time. A brown dwarf is a failed star, a body too small to ignite sustained nuclear fusion in its core. It is a cold, dark ember drifting in space. How could such a feeble object produce such intense, structured radio bursts? It was like expecting a dying campfire to power a searchlight. The signals were deemed impossible and therefore dismissed as noise from our own planet, a ghost created by human technology. This was a profound failure of cosmic imagination. We had discovered a radio lighthouse, but we refused to believe it could shine. We now understand that these forgotten bursts are a common feature of brown dwarfs with intense magnetic fields. These substellar objects are not inert. They are churning with convective energy, and in some cases they can generate magnetic fields thousands of times stronger than Jupiter's. The sporadic radio bursts are the sound of those magnetic fields snapping, of immense electrical currents short-circuiting in the object's atmosphere, creating brilliant flashes of coherent radio light. They are miniature, chaotic versions of pulsars operating on a smaller but no less fascinating scale. By dismissing these signals, we turned away from a perfect natural laboratory. Brown dwarfs occupy a crucial middle ground between planets and stars. Studying their powerful magnetospheric physics gives us a unique window into how magnetic dynamos work in objects that are not massive enough to be full stars, yet are far more massive than gas giants. This forgotten signal delayed our understanding of this entire class of celestial objects. It taught us that the universe can build powerful engines in the most unexpected of places, even within the cold, dark hearts of its failed stars. Deep beneath the South Dakota prairie, a forgotten tank of cleaning fluid was quietly listening to the universe. In the 1960s, this homely detector was one of the first to map the rain of cosmic rays striking our planet. Its data revealed a subtle but crucial bend in the energy spectrum of these particles, a faint kink where the number of particles at a certain energy level suddenly changed its rate of decline. It was like tracking the speed of cars on a highway and noticing a distinct shift in the traffic pattern at a specific velocity. This kink, which astronomers now call the cosmic ray ankle, was noted in the data. But with limited statistics, the finding was deemed too weak to claim a discovery. It was a whisper of a transition, and so it was set aside, a ghost in a vat of fluid. That subtle bend in the data was a roadmap to the origin of the universe's most energetic particles. The ankle marks a fundamental shift in the cosmic ray population. Below this energy, the particles are predominantly confined to our own Milky Way galaxy, accelerated by local sources like supernova remnants and trapped by the galaxy's magnetic fields. They are galactic cosmic rays, but above the ankle, the particles have so much energy that the Milky Way's magnetic fields can no longer hold them. These are the extragalactic cosmic rays, visitors from far beyond our galactic borders, accelerated by engines of unimaginable power in distant active galaxies or colliding galaxy clusters. The ankle is the shoreline between our galactic island and the vast intergalactic ocean. Its initial dismissal delayed our understanding of this cosmic border for years. We missed an early opportunity to ask the most important question: what colossal forces in the void between galaxies can possibly accelerate a single atomic nucleus to energies millions of times greater than our most powerful particle collider? That forgotten kink in a prairie tank was the universe trying to draw us a map, a simple line in the data that separated the local from the ultimate. Deep in the archival plates of the 1980s, a single infrared pixel near the galactic center briefly blazed with unexpected light. It was a transient event, a sudden flare in the heat signature of the sky that quickly faded back into the background hum of the cosmos. The official explanation was a simple one: a probable mirror variable star. These are aging, pulsating suns whose brightness naturally rises and falls over many months, and so this brief flash was catalogued with that mundane label and set aside, another solved mystery in a crowded field. Yet this classification was a profound misdiagnosis, a quiet burial of a stellar catastrophe. The forgotten infrared transient was almost certainly not a gentle giant's heartbeat, but a scream. It was the thermal echo of a star being torn apart. Our galaxy's core is dominated by Sagittarius, a star, a supermassive black hole with a mass millions of times that of our Sun. When a star wanders too close, the black hole's immense gravitational tides can stretch and shred it into a long, thin streamer of superheated gas. As this stellar debris swirls down into the accretion disk, it flares brilliantly across the electromagnetic spectrum, releasing a vast pulse of energy, including the intense infrared glow that was briefly recorded. Alternatively, the flash could have been an outburst from a previously unknown microquasar, a stellar mass black hole mimicking the violent behavior of its supermassive cousins on a smaller, but equally ferocious scale. In either case, the event was a masterclass in the hidden violence of our own galactic backyard. By forgetting this signal, we missed an early, crucial data point. We failed to understand the frequency of these tidal disruption events, the diet of our central black hole, and the sheer level of activity simmering in the dense stellar cluster that surrounds it. This single, misclassified pixel was a snapshot of the most extreme gravitational environment we can directly observe, a fleeting glimpse of the monster at our galaxy's heart taking a bite. It forces a humbling realization that even the most dramatic cosmic events can be reduced to a single, quiet notation in a logbook, a whisper of annihilation we once mistook for a simple, aging star. Even the constant, predictable drift of a spacecraft can hide a whisper of thermal truth. For decades, the twin Pioneer probes sailed toward the edge of our solar system, their trajectories tracked with meticulous care. Yet a persistent, tiny anomaly plagued the data. The spacecraft were slowing down just a little more than they should have been, as if an unseen hand was applying a minuscule, constant brake. This was the Pioneer anomaly, a puzzle that captivated and confounded physicists for years. The focus was entirely on the path, on the unexplained deceleration itself. But buried within the mountains of telemetry was another, quieter set of data that almost everyone overlooked. The onboard thermal sensors were recording subtle, rhythmic fluctuations in temperature across the spacecraft's bodies. These were not seen as clues. They were considered background noise, insignificant jitters in systems designed for grand celestial navigation. We were obsessed with the destination, and we ignored the hum of the engine room. The solution, when it finally emerged, was a masterpiece of simple physics. The pioneers were powered by radioactive thermoelectric generators, which produced heat as a byproduct of creating electricity. That heat did not radiate away from the spacecraft uniformly. Slightly more thermal photons were bouncing off the back of their large dish antennas than were bouncing off the front. This anisotropic radiation, this lopsided thermal glow, created a tiny but relentless push, a photon thrust that acted exactly like a constant deceleration. The thermal fluctuations in the telemetry were the heartbeat of this process, the direct signature of the uneven heating that was solving the mystery in real time. By ignoring this ancillary data, we delayed the answer for years. We were looking for a new law of gravity or a mysterious drag from dark matter, all while the answer was quietly broadcasting from the spacecraft's own skin temperature. This forgotten thermal signature teaches a devastatingly simple lesson. In our quest for the profound, we often dismiss the mundane. We hunt for cosmic ghosts in the data while the solution is warming our own machinery. The universe speaks through every available channel, not just the ones we deem important. How many other mysteries could we solve today if we simply stopped filtering out the whispers we have labeled as mere noise? From the lost pulse of 1928 to the thermal whispers of the Pioneer probes, these 30 forgotten signals form a secret history of astronomy. This is a chronicle not just of what we found, but of what we overlooked, a testament to the fact that discovery is as much about perception as it is about observation. Each ghost in the data, from the dismissed solar neutrino drop to the classified atmospheric gamma-ray flash, teaches us a profound lesson in humility. They show us that our models of the universe, no matter how elegant, are always incomplete. We build beautiful maps of the cosmos, but the universe has a habit of hiding its greatest treasures just beyond the edges we have drawn. The next paradigm shift, the next revelation that will shatter our understanding of dark matter or the fabric of space-time, is not necessarily waiting in some distant, unexplored corner of the sky. It is likely hiding in plain sight, buried in petabytes of data we have already collected and filed away. This journey through forgotten whispers is a call to action, a plea to re-examine our archives with fresh eyes and infinitely more open minds. The cosmos is not silent. It is a constant, murmuring conversation, still speaking in codes we have only just begun to suspect. The greatest cosmic signal, the one that redefines everything, may not be the next brilliant flash our newest telescope detects. It might be the faint, persistent echo we have been filtering out for decades, the one we finally, humbly choose to hear.